this course some formalism of quantum mechanics, right? And then we also looked at one problem where the solution of time-independent Schrödinger equation was possible, particle in a box. And the reason we start looking into essentially particle in a box problem is because we started with time dependent, Schrödinger equation, right? And then we said that, okay, for the time independent Hamiltonians, if H is not function of time, in that case, we can formulate the solution of time dependent Schrödinger equation. We can formulate it as from the solutions of time independent Schrödinger equation. All right, and so we were solving time independent Schrödinger equation for particle in a box, and that was effectively finite box with infinite walls, right? So we found phi 1, phi 2, and so on, the solution for that problem. And today we're gonna look at a so-called variational method. And the reason why we need this method is because turns out that the solutions for the time-independent Schrödinger equation not always possible analytically, right? So why is it the case? Because it's a differential equation, and not all differential equations are solvable analytically. It's similar to the situation with other equations that you are more familiar with, algebraic ones. So algebraic equations, as you probably know from high school, they can be solved for quadratic ones. They teach you in high school how to solve. And then what they don't teach you usually, but the solutions exist for cubic, quartic, but already at the fifth power, solutions don't always exist. Numerical ones do, but to write them as functions of coefficients, not always possible. So the same story is about differential equations. Not all differential equations have solutions like particle in a box problem. And to give you a very simple example, if we consider the potential that is not very far from the particle in a box, right? So if we have like the box sort of setup, we have the walls where potential is infinite outside 0 to L region. And inside the box, we don't have any more potential which is equal to 0. We have potential which is equal to alpha x, right? So this inclined bottom of the well. So in that situation, there is no solution that one can easily find. And we need, even for this simple problem of inclined bottom potential, particle with the inclined box, inclined bottom. For this case, we need a approximate method, and this is the type of methods that not only applicable to this problem, but it's applicable in general to actually any problem that looks like this, eigenvalue problem, time-independent Schrödinger equation. And that's the motivation, right? So it's a very powerful tool that one can use if they don't know how to solve the differential equation analytically. Any questions regarding the motivation? So this is our potential. This is Hamiltonian. But as you will see, the method is applicable to anything. That just with few restrictions, that the Hamiltonian needs to be with a bounded spectrum, meaning that the energies that we get in this equation, they're bounded from above or from below. And if that's the case, then the variational approach can be used. And another, so restrictions are H has bounded spectrum, and number two, H is Hermitian. Okay. Now, are these conditions clear? If they're clear, then let's see if that's indeed the case. Tell me the example of the Hamiltonian with spectrum that is not bounded. Tell me tell me some examples that violate these two conditions. Either both or one. So if you cannot tell me the examples, that simply means that you probably don't understand what these properties are. So this is the check. Okay, so the example of the unbounded spectrum is a free particle, because free particle in principle has a spectrum that goes from minus infinity in momentum to plus infinity, so it's not bounded by any finite value. And non-Hermitian Hamiltonian, you could take, well, let's say d over dx. That's the operator that is non-Hermitian. And you could use that as an example of non-Hermitian operator. Okay, so let's continue with the variational method. It's based on the variational theorem. Essentially, it's a very useful statement that talks about expectation value of the Hamiltonian, right? So this is the expression. If we take some function which we don't know yet, right? So it's a trial function, and we put this function in this in the expression written, then that's the expectation value of the energy that Hamiltonian has. Now, the variational theorem says that with the Hamiltonian that is Hermitian and bounded, this energy is always above the ground state energy, so the lowest energy. And we can, in principle, find what is the ground state of the Hamiltonian by trying to optimize the coefficients in the description of our function as a linear combination of eigenstates for our Hamiltonian, right? So if we have eigenstates right there, then we know that any state is a linear superposition of those states, right? Now, here's another question just to check your understanding. Why do we know that any state, no matter what it is, should be a linear superposition of eigenstates of the Hamiltonian? And the answer to that question is because in quantum mechanics, we have all the operators, all the observables, Hamiltonian included, operators that are Hermitian, and they have complete spectrum, meaning all their eigenstates can be used to write any state that physical system can assume, right? So including phi x. So that's the answer to the question I asked. All right, so now if we use that decomposition for every state that we put, we could write it as a linear superposition of eigenstates. And it turns out that after doing some trivial algebra, which you can, of course, ask any questions you want, right? But if there are no questions, I would assume that this is obvious to you. Please let me know if it's not the case. I'll be happily explain the steps. But if that's obvious, then the solution to after this few steps where we apply the Hamiltonian to the eigenstates of its own essentially eigenstates, right? So, and in denominator we have as well integration of eigenstates which are orthonormal. Now, one question for checking whether you can follow the material is why the states that we have, the eigenstates we have, why are they orthonormal? And maybe let's ask simpler question, what orthonormal means? If anybody can answer that, that would be lovely. But if not, I will remind you that orthonormality is the condition when you integrate function with another one and you get 0 if functions are different, 1 if they are the same. So that's what orthonormality is. Now, why do we have orthonormality for the eigenfunctions? If you don't remember that, I will remind you that it happens because the Hamiltonian is Hermitian operator, and all the eigenstates of the Hermitian operator, they are orthonormal. We've proven the theorem. I'm not going to go and prove it again. Please look at the notes. And that explains why we have these symbols here, essentially because of orthonormality of our eigenstates for the Hamiltonian. Does anybody remember what these symbols are? Now, it seems like you need a little reminder what they are, or do you remember? So they are called delta Kronecker, and they are 0 when n not equal to m, and 1 when n equals to m. All right, with that, we obtain the following simple expression that tells us that expectation value of the Hamiltonian, the expectation energy, if you measure it in an experiment, that's the average of the distribution, will be equal to this expression where anybody can tell me what the CNs are and what ENs are.
Is Cn the probability density and then the En is the energy?
Well, isn't this energy? Is this symbol is energy?
Isn't that the average energy?
Yeah, so this is energy and this is energy. And what's the difference?
Or the one with the brackets is the average energy, correct? And then the En is the different components that are added together.
So these are called eigen energies, right? So it's a spectrum of the Hamiltonian. So this was the definition, right? And this energy is average energy that you get if you do the measurement of the function that we started with, phi of x, right? And you measure the Hamiltonian. In every instance, you measure these energies that are eigenenergies. And if you average them according to this expression, which is written explicitly here, you will get the average energy. Now, regarding the coefficients here, they are given before. So they are coefficients in the decomposition of the function that we started with. And that function is completely arbitrary. So we're starting with arbitrary functions, but since we assume that there are some eigenfunctions psi n, so these coefficients could be obtained by doing the projection of the phi x function on the eigenfunctions, right? Note that all this derivation does not require us to know what these guys are. And this phi function is also completely arbitrary. So the beauty of this derivation is that we don't need to know all these functions. We still can write that average energy will be equal to this expression. And this is similar to what we did before for the measurement problem, essentially. Now, if we, for simplicity, make an assumption that the phi function is normalized, right? So normalized function means that the expectation value has this in denominator, which is 1, and that is just a sum of Cn square. So this denominator is 1. In that case, the expectation value for the energy is simply the numerator. And now what we do next to prove that the expectation value is always higher or equal than the ground state energy. Here I use enumeration from 1 to up to infinity. So I'm assuming that I can always order energies in the ascending order. So E1, well, that's descending. So E1 is less or equal than E2. E2 is equal to less or equal than E3, and so on. So there is this ascending order of energies. And now I can see that because these coefficients are all positive, I can only make this expression smaller if I substitute En by E1, right? So if I take all Ens in this expression and I substitute them by E1, from that, let me write intermediate statement. So if I did that substitution, the expression that I got is only smaller, right? Because I substituted bigger numbers by the smaller number. And I did it so that I could further simplify, since this expression is, well, just simply E1, because these coefficients, as we pointed out before, due to normalization of the function that we are working with, these coefficients are just 1. And so with that, we've proven the variational theorem that says that expectation value of energy is always higher or equal than E1, right? Which is ground state energy. That's a ground state. Ground state being the smallest, right? So all other states are higher in energy. Okay, any questions regarding this proof? Because this is important, and let's see, why did we need Hermitian Hamiltonian in order to do this proof? And we needed bounded spectrum. Well, we needed bounded spectrum to write this. And we needed Hermitian Hamiltonian to be able to write essentially that, well, essentially this equation from 12 to 15, because for non-Hermitian Hamiltonians, then you don't have necessarily the eigenfunctions, which are the same applying from the right side and from the left side. Okay, so that's what we need for essentially for the non-Hermitian Hamiltonians. You may have two different eigenfunctions, whether you apply, this is from the left, get all left, well, some eigenvalue. The eigenvalue, let's say, is the same, or 1, psi L, and from the right, psi R. So these functions that are eigenfunctions of the operator, they are different. They in principle can be different if the operator is not Hermitian. That's why this derivation is based on assumption that Hamiltonian is Hermitian. Then all the eigenstates that we have for the Hamiltonian, they are the same whether you applying them from the right or from the left. And the right and left comes from, well, this expression, where here we have right side and here is the left side. Okay, so essentially the lesson is you should ask these questions yourself, right? So whenever some theorem is proven and the conditions are given, in principle, you should always ask yourself and then the teacher why the conditions were needed. And if you don't have an answer, you don't understand the derivation, right? So it's very simple, because then it's easy to check these things later on exam and homework, right? And so if you do these things always by yourself, then you will be ready to questions like that on the exam. Okay. All right. So what does this give us? This variational theorem that says that you can go below the ground state. It gives us a very convenient kind of statement that now if we're looking for, let's say, a function that we want to be as close to the ground state of the Hamiltonian, so we can do that by writing down this function in some form, well, let's say, to avoid the abstraction that is not necessary, and that's the reason why I've chosen this particular example, is if we are considering the box that is infinite, but we have somewhat different bottom, potential is slightly different, and especially if alpha is small, the potential is really close to what we already know how to solve, which is particle in the flat box, right? Then it makes physical sense to look for the solution of this problem as a linear combination of solutions that come from the particle in the box, right? So these guys here are solutions for problem with a flat bottom, the same box size, right? Same infinite walls that we considered. We know these functions. Everybody can write them as a square root of 2 over L sine n pi x divided by L, right? So this is the n dependence. We introduced them previous 2 lectures. And so now, if you have this sum with a few terms, you can look for the coefficients here and what would be the criterion to optimize or look for these coefficients. The criterion will be very simple. We would like to come as close to the ground state if we are trying to make this to be a ground state, right? So we cannot miss ground state. We always will approach that energy from above, right? According to this variational theorem. So therefore, we can optimize coefficients to minimize the expectation value of energy for the function that we constructed, right? So this is our cost function. And we can change and the coefficients become our new variables, right? So is the formulation clear? Essentially, this should remind you multivariable calculus, right? So when you have a function of, say, 2 variables, x and y, and you're trying to find the minimum of that function. Now, this is x and y, and the function is the third coordinate. So how do we do that? Do you guys remember? Did you take multivariable calculus? The sort of the approach to this problem is really similar to single variable calculus. You don't need to even worry about multivariable for now. How do we do this for the single variable problem? Let's say if this is a function and we are trying to find this type of function or this type of function. We're trying to find the minimum or maximum. How do we do that? And the right answer to the question I posed is you use derivatives. Yeah. So the calculus is convenient because we know how to differentiate. And what derivatives give us is conditions for the extrema, right? So the zero derivative means that we are in the either maximum or minimum, or in the multivariable case in a saddle point. Now, what we do in this problem is our coefficients are our variables, x and y, and more than x and y because we can have more than two coefficients. So in order to minimize or find the minimum of the expectation value now with respect to coefficients, we again write down our expectation value expressions. At this point, we already using functions that are not eigenfunctions of this Hamiltonian. So this series of equalities are different than this series of equalities because here we use functions that are eigenfunctions of the Hamiltonian. Since we were not doing the calculations, we were doing the derivation. And in this case, where we want to formulate what the energy functional is, right, or cost function is, we are using the functions that we have. We take them from the particle in the box function. In general case, we could take them from some problem that we know is relatively close to the one that we are considering. But it's somewhat an art to find the problem that is close to the one that we're looking for. And in the computer lab, you will see that in many molecular applications, in order to do this variational approach, the functions that people use are atomic orbitals in order to find molecular orbitals, and that's something that you have seen probably in the general chemistry even, right? So that's what chemists usually are considering. All right, so now with that, these other steps, you just apply the Hamiltonian to linear combination of that you represent your trial function, right? And you obtain this simple expression. Why is it simple? Because it has these coefficients, h and m, the matrix elements of the Hamiltonian with our basis functions that we know from the particle in the box problem. And this is our new operator. And because we use still basis functions which are orthonormal, we have simple expression between the for the integrals between the functions. Any questions so far about this derivation? Okay, so then I can ask, if you don't have questions, why don't we have stars in the definition of the matrix elements? Why do we ignore conjugation?
I'm just taking not a guess, but is it because they're guaranteed to be real numbers?
Yeah, this is what is written right there. We ignore complex conjugation because phi n are real. Why are they real?
Because they're Hermitian?
Functions cannot be Hermitian. Hermitian are operators, right? So functions are real, but Hermitian operators not necessarily have real functions as eigenfunctions. They are real simply because we solved for the particle in the box problem, right? And we know what phi and x is, or they are, right? So they are these functions, they are sine functions. We obtained them on the previous lectures, and that's why they're real, right? So because they are not arbitrary functions. We've chosen them to be real. That's the simple answer. Just checking whether you are following what is going on, because essentially all my questions are essentially about the quantity. The answers are already in the more or less the things that I said before. Okay. All right, cool. So that's why we can skip the stars, and that's why our matrix elements, they can be easily calculated since the functions are known, the Hamiltonian is known, and so yeah, so we could easily now formulate what this expectation value of energy is as a function of these coefficients. Okay, and so the expression, because of the delta Kronecker symbols here, the expression is like could be written like this. So we have coefficients and matrix, and this H and M are really constants here. Right. So now we need to, in order to find a minimum of this expression as a function of the coefficient, we just simply write that we need to find the derivative with respect to every coefficient for all k, and we equate that derivative to 0. This is, I don't know the level of your mathematical preparation, but the simplest I could go is in 1D case, if you have a y as a function of x and some parameter a, so you could find the minimum of this parabola, right? So this is like this, where x is either minus a or, sorry, x is either, where does it cross? So it crosses at 0, at a, right? So at a, it touches the 0, and then that essentially is a minimum, right? So no, so the graph would be like this. Okay. And so the minimum could be formally found by differentiating with respect to x and solving the problem x minus a equals 0. So x equals a, right? So now in our case, the function y is this expectation value of energy. Variable x is coefficients, and the parameter a would be these matrix elements, which are some constants. They don't depend on the coefficients, right? So that's what we do. In order to find the derivative of the ratio, because we have function expectation value is just a function of coefficients f divided by function of the coefficients in the denominator g, let's say. And so for simplicity, we could write first, how do we differentiate the ratio? And if you follow this differentiation steps, which are technically not that difficult, the only thing that one needs to remember is that once you start differentiating, there is a ratio f over g, which is our original expectation value, right? So it's convenient to separate it, because instead of carrying f over g. So then, going further in this exercise in calculus and differentiation, we obtain at the end the expression that looks like this. And if you think about it, if this is a fixed quantity, expectation value, then you get the linear system of equations for the coefficients. Okay? And so you get, for every coefficient, you get its own equation, so that you could have for every ck linear system of equation. And again, to avoid the level of abstraction, we could just consider the simple case where, let's say we have only two functions in this derivation. And these two functions have coefficients C1 and C2, right? So one thing to always remember is that we differentiate in this expression with respect to coefficients, not with respect to x. It's like this is one of those problems that x is not a variable that we differentiate in. Keep that in mind because we are trying to find function, we're not trying to find the minimum over the function, right? So that's why x is not really our variable to differentiate. We differentiate in respect to C1 and C2. Okay, so continue on. In this case of two functions, we have C1 and C2 as variables, and the system of equations that we get, it looks very simple. You could convince yourself that what was written before, it's simply boils down to these expressions, to a linear system of equations. And in order to resolve them, we, of course, for a specific case, need to put constants. For this situation is the h constants. They come from, as we were writing before, from the matrix elements of the Hamiltonian, right? So this type of integrals one can calculate, or computer can calculate. And in the case of problem that we are considering, which is again the box with the inclined bottom, right? So with the angle alpha, we have just this matrix, two matrix elements that the off diagonal and diagonal. You can check myself and derive them at home using the expressions for the particle in the box function. Okay, and then the rest, well, we have this system of equations, and those who study linear algebra know that this is just a problem where we have matrix H11, H12, H21, H22 multiplied by the coefficients. Those who didn't study linear algebra, then this is just effectively a problem of solving linear system of equations with condition that coefficients, they cannot be zero, right? So they both need to be, at least one of them needs to be non-zero, and therefore there are requirements to solve this problem that essentially tell us that we need to have linear dependency between the two equations. Otherwise, we cannot have non-zero coefficients. Do you need a further clarification why this is the case, or that was obvious for people who are listening?
Here, please remove any batteries.
Sorry, are we assuming, how did we get E average times C1 in the first one and then E average C2 in the second one? The equations, I mean. Sorry.
We obtain this from the derivation that we just did, where we differentiated, right? So we differentiated the expression for the expectation value of energy, and we obtain that the derivatives contain the expression itself. right? So let's say if your expectation value was a ratio between f and g, when you differentiate, and f and g are functions of coefficients, then when you differentiate the ratio, this is the normal expression for the derivative of the ratio, right? And then continuing on, you realize that this derivative, it needs to be 0. So that simply means that f prime g equals to f g prime, and therefore f prime equals to this expression, and f over g is the expectation value of energy. So therefore, the derivation of f with respect to the coefficient is equal to the expectation value of energy, dg over dck. So, putting all this together, you obtain the equation, essentially, that comes from this expression, right? So this results into f prime over g equals to f g prime over g squared, right? So that leads to the energy reappearing because this is the expression. Does that make things clear?
Yes, thank you.
Okay, so then essentially we are close to the end, and we can write down this linear system of equation and solve the so-called eigenvalue problem, because this is what it is. The solutions of these two equations, like these linear equations, they must be linearly dependent. Otherwise, the only solution is C1 equal to 0 and C2 equal to 0. So that's a trivial solution, which we don't want. But if we want non-trivial solution, then there is a linear dependency between the equations that we need to have. Otherwise, we will end up with a trivial one. And in order to have a sort of linearly dependent equations, the condition for that is the determinant of the matrix, determinant of this matrix. It needs to be effectively minus E identity. That determinant needs to be 0. And now the question is this obvious? Do I need to explain this part? Or you've seen this before?
Could you explain it, please? Thank you.
Yeah, okay, so if we have essentially a system of equations, in this case H matrix multiplied by coefficient, and we have expectation value of energy here multiplied by coefficient, right? So we could bring everything into one side, right? So that would be this is our new matrix, H matrix, minus the matrix where expectation value is in diagonal, right? So this is this matrix multiplied by coefficient equal to 0. So then clearly this is the matrix multiplying the vector, and we get the 0 vector. So the trivial solution is the coefficient vector is 0. We don't want that. And so non-trivial solution requires that the determinant of this matrix is 0. Why? Because if there is no linear dependency, then the only solution is the coefficient equal to 0. So that's why we are solving the determinant equation in order to find effectively the expectation value in order to well, to get the solution of our equation and find the coefficients.
So the determinant is 0 if the solution is non-trivial?
That's right, yes. In order to have non-trivial solution, the determinant needs to be 0. Because if there is no linear dependency, then the only solution could be 0. So the one way to easily see that, imagine you have C1 multiplied by some value plus well, 0, and then 0 plus, let's say we have a diagonal case, and these are 0. So for non-zero H11 and H22, we only can have C1 and C2 to be 0, right? So that's why the matrix H11 and H22 in this case, that determinant is non-zero, and that's why the only solution are trivial solution. Otherwise, we cannot have non-zero coefficients.
Sorry, where did H12 and H21 go? Is it because they're the delta Conacher condition? Or
No, this is a completely kind of made up example where you could see that if the matrix has a non-zero determinant, then the solution will be trivial. Now, in order to, I guess, explain this at the level that will be clear, can you tell me whether you know what determinant is and linear dependency?
for determinant, I know that like for it's a scalar value and it's calculated from like a square matrix that signifies that there's invertibility. But so like for like a 2 by 2, it'd be like ABCD AD minus BC. I'm not really sure, but I think I'm just having trouble like connecting the concepts between this and here.
Right. So essentially, if you have two vectors, let's say v1, v2, and u1, u2. So how do you use determinant to see if they are like this? So this is the v and this is u. They are collinear, or they are like this. So
If you would like to volunteer, please remove any.
is the question clear?
If you would like to volunteer.
Sorry, you froze for a second, so I didn't hear the question. What was the question?
The question is if you have two vectors on the plane, right? So one is v1, v2, another is u1, u2. So how can you use determinants to determine whether the vectors are linearly dependent? So they are collinear. This is the situation, or you have this situation.
I'm not quite sure. Could you explain?
Right. So this is what linear algebra course should explain. and or geometry in principle, that if you build the matrix V1, V2, U1, U2, right? So you build this matrix out of the two vectors, and then you calculate the determinant. If the determinant is 0, that means it's this situation. And if the determinant is not 0, then it's this situation. Okay, so that's kind of linear dependency of vectors. Okay, so I guess the easy way out of this, essentially, because of the lack of material in the geometry that you took before, let's just say that in order to solve the equations that we have here, right? So these equations, in order to solve this, there is a standard procedure that linear algebra teaches us. And because, well, this is quantum mechanics, not linear algebra course, I'm not gonna dwell into that. Simply, it's a standard material, and we probably won't need that anyway. So then we can just say, all right, we have a linear system of equation that is an eigenvalue problem that one solves using standard methods. One step in that standard method is to formulate the determinant that is based on the matrix H, right? So that we're given H11, H12, H21, H22. We subtract in diagonal this unknown quantity to us, the expectation value. We subtract it, and we write the determinant equal to 0. So we solve this with respect to the energy. And after finding energy, we are finding the coefficients which are not all 0 in the standard linear algebra packages. That's called eigenvalue problem. And for solving it, all you need is to give the H matrix, and the linear algebra procedure will spit out the expectation value and the coefficients C1 and C2. Okay. So if you want to know more, we could discuss further, but that probably would require me lecturing a little bit more on the linear algebra side of things, that to connect the concepts that linear algebra people are supposed to connect. Okay.
Why is only H11 and H22 subtracting the average energy value?
All right. So do you know how to operate with the matrices and vectors?
I think
Ladies and
so.
gentlemen, we do have
Sorry, I asked like, do you know how to operate with the vectors and matrices?
I did take linear algebra, but this was 2 semesters ago, so I might need a reminder.
All right, so since we out of time right now, let's start with this our next lecture on Monday. You will review some of the linear algebra concepts, and I will explain this more in details, and you could ask more questions because it will probably require work from both sides. simply because if I assume the knowledge of linear algebra, what I'm saying is sort of, oh, it's based on some statements, right? But because you don't remember these statements or didn't even study them, it's not clear what is obvious and what is not in this case, right? So it's a longer process.
Yeah, sure, sounds good. I'll bring any questions
Okay.
I have to you on Monday then.
Right. Please look at the notes that up there in the which I posted, and sort of we could discuss on Monday what is left there to understand. Okay.